Thank you for inviting me. I'm sorry for not being in person. I'm currently interning at Google in Seattle, so I'm not available in Ann Arbor. Today we'll be talking about this project that I've been working on for some time, and it comprises a couple of different projects. And I think we can view this in terms of two complementary dimensions. And I think all of this involves computer programs. The first on the left-hand side would be how we encode experiment logic. And I'm thinking that the way to do this would be to utilize existing programming languages like Python, for instance. I'll be talking about this in a bit more in depth. And on the other hand, we have the infrastructure, which is, in our case, because I work on computer systems in the computer science teams at UMich, this involves a lot of cloud infrastructure, as in things on AWS, Azure, or Google Cloud. And to be a little bit more precise on how we can express this as a computer program, there is this paradigm called infrastructure as code, where essentially you can encode all of your infrastructure in a very declarative fashion. So, for instance, if you want to instantiate a computer network, you would be using the last four lines here. This is a very simplified version. In practice, it's very complicated because it contains a lot of different specifications and so on. And at the same time, we have a new project within my lab at UMich where we're thinking about moving beyond cloud infrastructure and looking at potentially doing this same infrastructure provisioning and management using lab equipment. And I'm curious to know about your thoughts on this. So feel free to interrupt me throughout this presentation if you have any thoughts on whether or not this is actually feasible. Um, yeah, and also on that side, I won't be talking too much about that specific project since it's ongoing, but we're actually collaborating with some programmable lab companies like Emerald Cloud Lab at CMU to develop a prototype. So basically, everything will be expressed in programs, and you can basically run your AI agent to actually construct this experiment logic and then actually provision the infrastructure and run everything end to end. So there are four pillars to this, I think. The first would be on how we can train the AI agent to do this well. And the second is to potentially build some custom agent frameworks to allow them to do this experiment or group of experiments. And the third thing would be how we can evaluate these agents. And the fourth thing, which I won't be talking too much about, is to move beyond in silico experiments, because as you'll see later, I'm pretty much focused on experiments that you can actually conduct purely using a computer. So the first project is on training the agent. And this is a project that I just recently completed during my internship at Meta, I think last month. It's currently in submission to a conference, but I'm also going to be putting up an archive version later, I think maybe in a couple of weeks once I get approved. So the idea behind this project is because small language models, they're really bad at actually doing things well. Can we essentially allow them to collaborate with experts to be able to solve complicated software engineering tasks? So I will skip through this because this was meant for a different audience. But I think I'll just directly go into the background. So the first question we need to answer is why do we need to target small language models, given that we have all of these super amazing frontier models from OpenAI, Anthropic, and so on. So this is a paper that was published by NVIDIA, I think a few months ago. And basically, it's saying that SLMs, small language models, are the future of agentic AI. And the reason this is so is because they've found that SLMs are sufficiently powerful for a variety of different tasks. For instance, Phi, which was released by Microsoft, is really pretty much really good at doing common sense reasoning. And at the same time, SLMs are very economical for agentic systems because in terms of both inference efficiency and in terms of the training efficiency, and which is fine-tuning agility that I wrote here, it's very fast compared to training a frontier model. And thirdly, because agents typically only expose a very narrow LLM functionality, you don't necessarily need to bake so much, broad knowledge into this model. So this is what frontier labs are doing. They're baking in as much as possible into these models because they're general purpose. In our case, it's domain specific, so there's no need for us to do, and especially when you consider real production use cases where, um, in this, let's say, an agent that's tasked for performing some kind of experiment, you might have multiple agents inside the system, and each of them are only tasked to do very specific things by utilizing very specific tools. And so there's no need for you to have so much knowledge to begin with. So a couple of examples in Microsoft's 5.4, they've been able to basically train this model to do very well in single-turn QA tasks. So at the very bottom, I'm showcasing an example task here. It's a question, multiple choice question, answer. Yeah, very simple. And we have other papers from Microsoft as well. And this one is basically training a model using reinforcement learning to do really well on some pretty competitive math competition tasks. And on the right-hand side, you see an example process that this agent would need to take to solve this. So you can see it's a question at the very top, and then it needs to do a lot of different reasoning steps, deriving equations, and so on to be able to find the actual answer. So this is a step up from the previous project. At the same time, we have this company called Hugging Face. You might not be aware, but Hugging Face is like an aggregator for different models and things like that. But they also have a research team that trains models as well. And in Hugging Face, they're able to do this for coding. But in coding, what they're doing is simple single turn, uh, I guess, questions from quizzes, for instance. So here you can see this question is very simple. It's saying, write a Python function that does this, that satisfies these test cases, and the model just returns this answer in one turn and then exits, and that's it. Very simple. So this is not an agent, it's a model that does a particular task. So what we're concerned about is multi-turn long context agentic tasks. So the specific task that we're considering is focused on software engineering tasks. But I feel like the same principle should apply to experimental tasks as well, because you can imagine you're writing programs and you're executing them and you're iterating on them based on the results that you obtain, and so on and so forth. And so the reason we target software engineering tasks is because we have this very nice benchmark developed by researchers at Princeton and Stanford called SweBench, which is really suitable for this. And it's really well recognized, so it's a good target for us. So basically, in this task, what you have is a GitHub issue derived from some very popular GitHub repository. And the language model would basically, write their program after multiple turns, and then eventually submit this. Upon submission, it will be tested against some unit tests provided within the task itself. So in particular, you need to develop an agent to run uh, as a front end for this language model to solve this task. And the most popular agent right now for SweBench would be SweAgent developed by the same team. So in SweAgent, what this LLM backbone has on the left-hand side, which we call LLM agent, has access to is essentially a set of tools that we show in the middle here. And these tools include tools to navigate the repository, search files, view files, edit files, and so on. And upon calling a specific tool, it would be directed for execution within a isolated terminal. And this terminal gives it access to a baked-in file system as well, which includes the repository. And so upon execution, you get back some output and you iterate. So that's why we call this an agent. So moving into our actual project, we found that existing small language models perform really poorly on Sweetbench. And if you look into the middle part here, you see that these are basically open weight models. I'm only including post-train models here, which is a final step that you do before you productionize the model. And we see that the state of the art, the SOTA, is SweAgent LM32B, which is actually developed by the SweAgent team just now. And the score that they have is 40.2%. Whereas if you look at small language models here, none of them perform well up until our system. So we call this SWE Protege, and it's a 7 billion parameter model that scores at max 42.4%. And this means it exceeds the performance of the previous soda, which was published a few months ago. So the motivation for our work is we found that utilizing the same data set. So what I mean is we're utilizing the same data set from Smith, which is another project that essentially provides high quality data sets that you can use to train models. And it was used to train the previous SOTA that I mentioned just now. And if we use this to train an SLM, what we find is that the performance actually regresses. And we actually did this by reproducing the results using the same methodology from that paper, Smith. And as you can see here, as you increase the number of dataset rows that you use to train the model, the performance goes up from 15.8% to 17% and eventually degrades to 13.4%. This is optimistic. The lowest score that we obtained was like 11%, so it's pretty bad. And in contrast, the larger SOTA model has a pretty much very nice log linear curve until 40.2%. So upon further analysis, we find that the small language model, which is shown in orange here, is actually really bad at making progress. So it always gets stuck. And you see that in the very middle here, one of the main failure reasons is that it aborts due to runtime limits. And we don't have an example here, but if you look at the actual agent trajectory, what you will see it's basically just calling the same commands over and over again, not knowing what actually to do, and eventually exiting. However, we see that small language models are actually pretty coherent because if you look at the sample trajectory here, uh, so let me explain. In line 884 here, this is the model's thought process. So it's saying, hey, let me search for a relevant section URAP. And it's calling this tool using line 887 here. And the observation here would be, I guess, the output from this tool. And you can see that it continues, it understands the output. In line 898, it's saying, great, let's look at this method since that's where the error seems to be occurring. And so you see that it's able to use tools, it's able to, do some basic reasoning properly in line with the previous works that I showed from Microsoft and so on. So what we're trying to do is basically post-train this model using a combination of supervised fine-tuning and agentic reinforcement learning to be able to do this task, to be able to make progress and solve the task. And the high-level idea is to augment this small language model with an additional tool call that it can use occasionally as it thinks it's needed to an expert. So this expert could be a frontier model or something else, or it could be a combination of different experts. And so I'm going to explain what this looks like on the very left side. You can see in this agent system, we're reusing SweAgent. You can see that we can add a single tool and use a strong language model to generate tasks that we can use for supervised fine-tuning against our SWE Protege 7B parameter model. So we're sourcing from the same data set, Smith that I mentioned earlier. And after this process, we would use GRPO, which is a specific algorithm, which is very popular right now for agentic RL, to do additional post-training. And the innovation that we have here is, in addition to the traditional reward function signals that people use, which is essentially test and similarity reward. So test reward is basically if the model is able to get all of the unit test cases that I mentioned earlier correct. And similarity is this more lenient reward where you give it partial scores if the patch produced by the model is relatively similar to the ground truth patch. We augment this with some trajectory level reward signals. So there's two kinds. The first kind is what we call a stall reward. And in this case, basically, uh, we monitor the model's progress within this agent trajectory and see if it's essentially stalling. The way to do this is basically to use like regex file matching, for instance, to see if it's repeating the same base commands, for instance, grep calls, cat calls, and so on. And then basically giving it a low score if it does this repeatedly. And a collab reward is given we repurpose the expert itself to serve as a value model. And basically, it gives us a score if it thinks the small language model is basically calling it appropriately, following instructions, and so on. So, to give you an overview of what this would look like, if you look at the left-hand side, we have a before image. So before we do this post-training, you see that our small language model is basically doing things that are pretty incoherent. So in step 10, it's reading some unrelated file. In step 11, it's editing some unrelated file for some incorrect reason. And in step 12, it's browsing unrelated directories. And in step 13, it believes it found the issue and solved the problem. And in step 14 to 75, it's basically repeating base commands, which is stalling. So after we do supervised fine-tuning, you can see that it still makes some occasional errors. But in step 11, it understands that, okay, maybe, I should call an expert right now. It basically asks a question, do you have any ideas? I'm thinking X, Y, and Z. Do you think this makes sense? And the expert responds by saying, okay, I think you should do A, then B, and update me. So it gives it a sequence of instructions to do based on its insight. And so the model here does only partial bits of it. So it does B, and it claims to have completed this, and it continues by stalling. So we solved this in agentic RL by asking the model, training the model to be able to follow through on every single instruction provided by this expert. As you can see in step 12 on the right-hand side, it does A, it does B. It understands that it completed this in step 14, and it also tries additional things before it reports back to the expert and says, okay, I finished everything, I did this and that. Um, I think this is the issue. Do you think this is reasonable? And what this does is it preserves the small language model as the main um, principal decision-making agent and offloads critical points to an expert if it needs it. So I'm going to go through a couple of high-level results. We're able to show here, and this is in after supervised fine-tuning only, that we're able to basically match the SOTA's performance across many different expert models. So in terms of the expert, we were using some Anthropic Claude models, Sonnet 3.7, 4.5, and Opus 4.1. And we're utilizing the same exact methods that the other SOTA papers used. We were also able to show that we can incur very little cost in terms of tokens, especially after doing agentic RL, because the model no longer stalls. So you can see that in terms of savings, from blue bars to green bars, we're able to save a lot of tokens. And we're able to maintain the number of expert tokens used at a pretty low amount. So the max here is around like 12%. That also shows that the small language model is doing most of the heavy lifting. And on the right-hand side, if we actually look at the cost itself, so um, for 3 Protege 7B in the legend, uh, what this is we're measuring the expert's cost used within this small language model, whereas with the purple and blue bar, we're basically showing an example if you were to use this frontier model itself to solve this task end to end. And you can see that the cost incurred by our models is very much, much smaller. I think up to 8x. And if you look at uh, the red bar for C Protege using Opus 4.1, which is a very expensive model. I think it's around 5.5x more expensive than Sonnet 3.7. You can see that even in that scenario, our model here only incurs a cost that is comparable to using Sonnet 3.7 for the entire trajectory, but still significantly lower than Sonnet 4.5, which is also 4x cheaper than using Opus 4.1. So overall, we're able to save on expert costs as well. So this is pretty critical for many different use cases where you're kind of constrained on frontier model cost, and you're trying to optimize in terms of achieving comparable performance, but using a very, very small amount of tokens on experts. So there are a couple of other results, like we're able to achieve reductions in stalling. I'll skip through all of these things, and I think we can jump into Curie here. But before I go into this, I was wondering if anybody had any questions for now. If not, I'll just, continue. Okay, cool. So Curie is basically our preliminary attempt at basically building an agent to work on some different in silico experiments. And we're essentially targeting AI research. And Curie was published, I think, in like Jan 2025, but it has now been like outdated, so it's completely eclipsed. But I'll just go through the high level idea uh, because it makes sense. Because it's eclipsed because agentic performance has basically, increased so much that you don't really need a framework like this anymore. So the idea behind this paper is we're thinking that experiments are basically the bottleneck in the entire research workflow. And the reason is because in our experience, doing lit review and coming up with the idea is pretty fast, but actually answering some questions using experiments is actually quite slow. And our work is inspired by a line of work by other people. In particular, we have this Sakana AI, which is a startup which received a lot of money based in Japan and one of the papers that they wrote, which is pretty popular, is basically building an AI scientist that they claim. It's just a toy project, but it's still very impressive on paper. And there's this other project by, I think it's pronounced Zoki, and they were able to basically write a paper, high level idea here, I'm showing on the screen, which was accepted by a natural language processing conference, ACL. I believe it's a workshop in that conference. So it's still pretty impressive. Um, yeah, right. So experiments are the bottleneck, as we mentioned. So you need to set up the experiment, you need to execute it, and so on, collect and analyze the results. I'll skip through the workflow because I don't think it's that relevant anymore. And we have a second agent that we're developing as well. And in this agent, we're actually trying to use models to provision the cloud infrastructure, which is the experiment infrastructure that we mentioned. And this is still ongoing work, but we have a preliminary paper that was published in ACM SIGOPS Operating Systems Review. And here, we're basically looking into the different modalities of how you provision cloud infrastructure. I'm not sure how this is done in different domains, but in cloud infrastructure, you have a few different ways to do this. The first way is to use what we call a provided SDK. And basically, an example of this is imagine that they provided a Python library for you, and you basically um, import this library within your code, and then you just provision that. That's one method. The second method you can do this is to use the CLI, which is the terminal, and you can basically enter commands in the terminal to provision different things like a virtual machine, for instance. The third method is to use IAC, which is infrastructure as code. I mentioned this at the very beginning of the presentation. And this is the current SOTA in terms of how you provision and manage cloud infrastructure, because it's a very neat declarative format. But at the same time, behind the scenes, it handles a lot of those complexities in terms of scheduling and making sure you don't do any incorrect actions that might hurt your existing infrastructure. And it prevents things like infrastructure drift from happening, where the state of your infrastructure has changed from your previous provisioning step. So I'm assuming that this holds in a lot of different other kinds of lab infrastructures, lab instruments, and so on if you're trying to automate it. But you can correct me if I'm wrong. And the fourth method is using a web console on a browser. And so you can click on different things and do this. It's very slow, but it is very visual. So it's easier for you to see if things are going wrong. So in here, we're thinking of combining all of these modalities because you have agents right now built by Anthropic and OpenAI, which, for instance, are very good at targeting the web browser environment. And there are some which are pretty good at, targeting terminals and writing programs and so on. So can we combine all of these things to build a unified agent? So this is just to show you that different modalities have their own benefits. So for example, in the web browser, the level of abstraction here is the highest. So the user's role and expertise in managing cloud infrastructure would be very low. They don't need that much expertise, and they can observe a lot of things. However, the success rate is very low because it hides a lot of problems that is really hard for you to debug later in case you're not able to actually provision the infrastructure. And it's also very low efficiency because you have to manually press things. So we have a basic framework. And in this framework, what we're doing is a general framework where we have an agent interface which connects to the user, and the user talks to this interface in natural language. And we do some prompt optimization here, which is eventually enters this orchestrator, which contains, the typical things in agents like memory, tools, reasoning, and planning. And it eventually boils down to some kind of action, which goes through a couple of guardrails to make sure that these actions are actually appropriate to this user in terms of, for instance, access control. Maybe the user isn't given access to perform a specific action to provision some specific infrastructure, maybe because the infrastructure is in use right now by some other lab mate or something else. And eventually goes into our agent cloud interface that issues API calls to the specific cloud vendors that control the infrastructure. So in terms of a lab setting, the difference here would be you would be replacing the tools that you provide to the agent a little bit. And you would also replace the cloud vendors here with the actual vendor. And in our case, this would be something like Emerald Cloud Lab, which is the same, kind of like the same thing here, but instead of having those virtual machines and so on, you would have access to lab instruments. So moving on, we're going to be talking about how we can evaluate these agents. So the first paper that we'll be talking about is on IAC eval. So this is to measure agents' performance on solving these infrastructure management tasks. And this was published in Europe's 2024. So the motivation for this is because cloud infrastructure management is very difficult. On the left-hand side, you have many different use cases by many different companies. So Home Depot, United, P&G, and so on. Everybody uses cloud infrastructure. Um, and so the different kinds of infrastructure that they need, the nuances there are completely different. And that's why it's a very big business, cloud infrastructure. And in the middle, you have many different kinds of cloud services. You have, as I mentioned, virtual machines, databases, and so on. And on the right-hand side, you have different kinds of requirements in terms of governance, security, and so on. So this means it's very hard for you to build an agent to be able to solve everything. So we want to measure that. So I mentioned just now that ISC is the SOTA, but at the same time, it's still quite difficult to build, even for human experts. So the first con is that it's actually non-intuitive because you're using a domain-specific language to do this. In this example here on the left-hand side, we have something called Terraform. So Terraform is this SOTA tool that provides the HCL language. You have some different languages from different cloud providers as well. And I think that eventually when programmable labs become even more popular, which we do see right now with some companies like Periodic Labs and Lilac Sciences and so on doing this, um, we can imagine that the interface, the language that is provided by these different players would be likewise quite different. So I think that one thing we need to do is to unify them, but that's a separate question. So the second con is semantic gap between the ISC layer and the actual cloud internals, because the user is only writing ISC and everything under the hood is, kept hidden. And this actually surfaces many different problems that the user ultimately needs to solve. We have a different paper on this. I'm not going to cover it right now. And hence, in companies right now, you need entire teams dedicated to doing infrastructure provisioning. So you can imagine you have a separate team where it consists of typical software engineers, and then you have another team dedicated to doing infrastructure management. We call this DevOps. In the future, for lab equipment, I'm assuming that this would be somewhat similar as well. And no existing benchmarks exist. And so we basically developed one which consists of many different tools, many different services within the cloud provider. For example, VPC and so on. But we don't need to know the details here. And we have a workflow in terms of how we provision this and evaluate this. So in the first step, the LLM basically gets a prompt from our data set and it's prompted to generate an ISC program. And from there, we utilize Terraform's existing compile checks to make sure that this program is syntactically correct and somewhat semantically correct as well. And in addition to that, we have a separate step which uses a specification that we provide to do intent matching to make sure that the semantics are correct. So to summarize, we have the syntax checks to make sure that the program is syntactically valid. And obviously, if it fails, it's incorrect in this step. And on top, we have the intent matching to make sure that it's semantically correct. So it fulfills what you intend for it to do. And if both cases pass, then it's correct. So here's an example of what this does. Um, we have a prompt at the very bottom. It's decently complex, even though it's still very simple. Uh, so you're trying to provision some uh, cluster which does something, and this cluster has different components inside it. And this cluster also needs to have different kinds of configurations that are specific for it. For example, you should only close connections that have been active for some given set amount of time. And it also needs a database, which is a separate component that serves a specific version and configuration for some Microsoft SQL Server. And it needs to be backed up every day and so on. And so on the left-hand side, you see a simplified correct configuration instance, which contains the database itself and the some other kind of database cluster. And on the right-hand side, you see the intent specifications, which is uh, written in another domain-specific language. So there's this thing called Regal, which is baked into some kind of intent matching engine you can imagine. And so here we mention things like, okay, for this AWS DB proxy resource, we need a specific attribute to be contained within this inequality. So 1,800 would correspond to 30 minutes and 3,600 would be 60 minutes and so on. So that's how we do it. I don't have too much time, but I'll go into the last project here, which is another benchmark, but targeted towards the experimental logic itself. And in here, we're targeting specifically AI research experiments, which can be completed entirely within a computer. And this is a paper that we did in collaboration with many different institutions, and it was recently accepted to iClear 2026, which is a machine learning conference. And here, the workflow is basically you have a data set, and in this data set, you have a question that you give to the agent. The agent is also provisioned with some high-level method on to give it some direction on what to do, and the agent is given some starter code. And all of these questions are extracted from top-tier machine learning papers. And in the middle, you have this agent, which we are utilizing some existing agents. Um, and you can imagine that the agent is given many different things like the dataset model, parameters, metrics, and specific access to some kind of hardware. The agent produces an implementation in addition to the design that I just mentioned. It's executed and the agent derives some conclusion from this. And eventually we evaluate this using some specifications that we provide. And this includes, I think, some unit test cases as well. And eventually we derive the performance of the agent in terms of different metrics. So we have a metric for the design component. So we measure if the agent is able to design the experiment well in terms of parameters and so on. And we measure if the agent is able to get the implementation correct in terms of the code itself. We measure if the code execution itself is successful or not. And then we check if the conclusion is correct or not by doing some kind of similarity semantic checking. So an example of this task would be you have some agent input, which is the question, the method at the bottom here, which talks about, like if this is a training task, it would talk about the data set to use, the number of epochs and things like that, which is hyperparameters in machine learning training, and the way to evaluate this. And the agent basically goes on and does this thing, but the ground truth itself is on the right-hand side. So on the right-hand side, you have the experiment design, which is specified in natural language. Um, the instructions itself are also in natural language. The implementation itself is also in natural language, but in code. And the expected outcome is also in natural language. So you can imagine the way to evaluate this would be to use an LLM to check to see if things are correct. And in practice, we noticed that the LLM is able to do this really well because the ground truths that we provide are very constrained. So there's not too much to look at. So it's quite easy. And in addition to this, as I mentioned, we also check for execution correctness, which is we need to run the implementation in some fresh environment to make sure that it's correct. And yeah, if it's correct, then that metric is considered correct. We consider many different papers in different domains, including deep learning, RL, different applications, computer vision, and so on. And we have a workflow, but I don't think we need to go into it. But the high level idea is we're able to construct our data set in a semi-autonomous way. So we utilize our own custom agent system to do this. And we interject some human checking in between the steps to make sure it's correct. And we just keep refining this process until we get the task. And yeah, so semi-autonomous, this is important because in machine learning, you have many papers. A lot of them are actually kind of bad. So you want to get the good ones. And in addition to that, you want to make sure that you can actually reproduce the results from them. Um, so it's really difficult for you to do this um, by yourself. OpenAI had a paper before us where they did this manually and it took them a long time to do. In our case, it's semi-autonomous, so it's much faster in case you want to adapt this to some new domains or new papers that come out in ML, since it's a very um, like fast domain. Yeah, and in terms of our results, we show that current, not current, this is outdated. Uh, the best model that we observed was O3 Mini, but this is so long ago. Yeah, it still is pretty bad. The max accuracy, if you include every single metric, is 0.5%. Um, but individual components are pretty good. Yeah, that covers everything.
Anyone have any questions for Patrick? We'll give it a few minutes. Oh, yep, we got a question, I think.
Um, Great talk, by the way. One of the questions that I had was you mentioned, many times talking about these different benchmarks that they get outdated in a matter of like a few months. But in terms of the basic framework of using an agent to design experiments, do you think that the same principles will apply to um, new sort of generations of agentic AI, or are there fundamental shifts in how we need to design even that interface?
That's a great question. Thank you. I think that I would clarify a little bit. I think the benchmark itself is still valid, but rather the results that I have in the paper are invalid now because they're outdated. Because the models that we're using are pretty old. Um, I think we need to test this on newer models. But the principles on how we construct the benchmark, I think, are pretty valid. I think we're the first benchmark to really consider many different metrics because if you only consider, for example, if the result is correct, then obviously this would not be a complete picture. I think that considering multi-metric benchmarks is really important. But I think that innovations on how we construct the actual ground truths itself within each individual metric might need some additional improvements. So right now we're using natural language, and at the same time, I didn't mention this, but the task itself is a little bit constrained because um, the exact steps that need to be done they're largely specified in the agent input. However, ideally, you want to allow for some creativity or open-endedness by the agent who's running the task, because maybe the agent thinks there's a different kind of method to use to be able to derive, even better results than we thought about. But we don't consider this right now. Um, so that's what I think we can improve. In addition to that, I think that we also need to apply this to different domains. We haven't really tested it, but I believe it should still hold as long as it's in silico. We haven't really developed a benchmark for some uh, tasks that it consider actual lab instruments yet. But that's also because we don't have a proper programmable framework to do this really well.